Okay, welcome again. Let's continue with the new chapter, Exergy. Now, the concept of exergy is very different from the concept of the energy. Now, the first question is, if we have one unit like energy, why we need to define a new term, exergy? To answer this question, sometimes the energy, only energy can be misleading because when we apply first law of thermodynamics, that is based on the quantity of the energy, right? Which says that the energy remains constant. It can take form from one form of the energy to another form, so energy is conserved. But sometimes, like let me give you some example. For example, if we have, let's say, 100 joule of electrical energy, and there is another type of the energy we call the thermal energy, and we have the 100 joule of thermal energy. Now the unit and the quantity of the energy is same, but what about the work potential? What about the quality of the energy? Obviously the electrical energy has a higher quality. Like if you have 100 watt of the electrical energy, you can light up several led, right? Whereas the 100 joule of thermal energy, you cannot get some more work output from that energy, right? So that means the quantity of the thermal energy and electrical energy is the same, but the quality is not same. So that's why sometimes the unit of energy can be misleading. So we need to define another term. We call it at exergy, which covers both the quantity of energy as well as the quality of the energy. Let me give you another example. For example, if you have two gas cylinder, which are, one is filled with 1 kg of air, 20 degrees C, and 1 bar, right? This is a larger cylinder. If we have another smaller cylinder which contains the same gas, 1 kg of air, 20 degrees C, but the pressure is 8 bar. Now assume that you consider air as an ideal gas. So what do you think in terms of the energy? Which cylinder contains more energy, right? Obviously most of the student will say that this smaller cylinder will contain more energy, but this is wrong, because once the air is an ideal gas, then the energy contained is internal energy, and internal energy is a function of temperature only. So U is a function of temperature only, right? U mean internal energy is a function of temperature only, since the temperature is same in both the cylinder. So the internal energy in the larger cylinder and internal energy in the smaller cylinder is same. So now you can see the quantity of the energy in both of the cylinder is the same. But what about the work potential? Ability to perform work, ability to give you some work output is different in both of the cylinder. Now, when we say the ability to perform some work output, it is always described with reference to some ambient condition. Now if the both the cylinder has the same ambient, let's say the ambient temperature is T naught, pressure is P naught. So when we say the work potential, then the work potential of the smaller cylinder is more than the work potential of the larger cylinder, because the pressure gradient is more, right? The temperature gradient will be the same in smaller and the larger cylinder, but the pressure gradient of the smaller cylinder is higher. So that's why the smaller cylinder will have more capability to perform to give you some work, useful work, right? So therefore the exergy of the smaller cylinder is higher than the larger cylinder, but the quantity of the energy is same, right? Let me explain with the help of another example. Like let's say there is a fuel tank which is initially filled, and it is outside, it is filled with some air which is initially at temperature T1, right? And the both the fuel and the surrounding is contained in an isolated system, right? Isolated system mean no heat, no mass can flow out of this boundary. Now let's say we light up the fire. So initially the fuel will start burning, right? And the temperature of the air, this air will start increasing. So that means this energy is changing form from chemical energy to heat energy, right? Eventually all of the fuel will be burned, and the air temperature will be very high. I mean, from initial temperature, now the final temperature is Ti plus delta T. Now you can see the quantity of the energy is the same. Whatever was the initial energy, I mean calorific value of the fuel, now it is converted into heat and the thermal energy, right? The quantity of the energy is same. What about the quality of the energy? Now the quality of energy has decreased with the passage of time, because initially the fuel, it has a high economic value, it has a high quality of the energy. With the help of fuel you can perform many functions. You can use that in automobile, you can use that for any combustion application. Whereas the hot gases, I mean these gases, although these hot gases has the same quantity of the energy, but their work potential has decreased, the capability to perform work has decreased, right? I hope you understood the concept of the exergy. So exergy is basically the work potential of the system with reference to the surrounding. Okay, now let's say if this is the system that has some exergy, and this system has some surrounding which is at temperature T naught and pressure P naught. Now in order to get some useful work from this system and surrounding, you must have some heat engine or a power cycle. That heat engine will take heat Q from that system, then it will convert that heat into some useful work WC, right? And one part of the heat will be given to the surrounding, right? So surrounding is must for getting any work potential, right? Now let's define the exergy now. So exergy is basically the maximum theoretical work obtainable from an overall system. So overall system mean the system and the surrounding, right, with reference to some environment condition. Okay, and environment condition or the reference condition is very important. Normally we take temperature as 25 degrees C and pressure and 1 atmospheric. Normally we represent that P naught and T naught. These are the ambient condition. P naught and T naught is the reference state. So whenever we want to calculate the work potential or the exergy of a system, it is always calculated with reference to some ambient condition and with reference to some to P naught and T naught. And what is the dead state? When the system, let's say this is the system, and system has temperature, let's say T, and pressure has P, right? And the system has some environment, let's say environment temperature is T naught and pressure is P naught. So when the system and the surrounding, they are in thermal and mechanical equilibrium, then we call that system to be in dead state. So that state means there is no temperature gradient, there is no pressure gradient, we cannot get any useful work from the system. So that state of the system is called the dead state, right? When the ambient and the system has same temperature, same pressure, so that state is called dead state. At dead state, exergy of the system is zero. Now there is another confusion regarding the concept of the exergy. Let's say there is the total energy from any system. Let's say this is the any energy, which is the total energy, right? So that total energy, basically it has two components. One is the availability, another one is unavailability. Availability mean exergy. So sometimes we also called exergy as availability, right? So this is basically availability, and the other component we called unavailability, right? Unavailability is that part of the heat which we have to supply to the ambient, right? This is must, because we cannot create any system, any device which is free from that. We always have to give certain part of the energy to the sink, right? I mean, according to second law of thermodynamic, one part of the heat we have to provide to the sink. So this is that portion, unavailability. I mean, this is the that part of the energy that we give to the ambient, to the surrounding, right? We cannot avoid that component. Yes, we can minimize this component, but we cannot avoid that component. As an engineer, our effort is to minimize that component, right, to utilize more energy. I mean, availability part should be as high as possible, and this unavailable part should be as low as possible. Now within that availability, in that portion, right, it can have some irreversibilities. I mean, the causes of the irreversibility could be many. It could be because of mixing, it could be because of heat loss. So there could be one portion from that availability we call because of the irreversibilities, right? Because of the irreversibilities, right? So basically it has three component now, right? It has three component now. I mean, total energy. One component is the unavailability, right? Second component is the availability. So within that availability, it can have irreversibilities, right? So depending upon the rate of the irreversibilities, right? Now, if we talk about the significance of the exergy, I mean, why the exergy is so important, right? I'll give you two examples. One is for the gas turbine, and the other one is for the steam turbine. Let's say if we talk about the gas turbine, now you can see gas turbine has three components: compressor, combustion chamber, and turbine. Now, when we try to apply the exergy, we will try to see where the useful work has destroyed. For example, let's say if we try to apply on the compressor, we'll see how much is the exergy of the air entering into the compressor and exergy because of work input, right? So this is the input exergy. That should be ideally that should be equal to the output exergy, right? But because of the irreversibilities, input exergy will be different than the output exergy, right? So what we will see how much is the exergy destruction in the compressor. Similarly, when we'll move to the combustion chamber, so how much exergy is entering into the combustor chamber, and similarly how much fuel exergy because of fuel is entering into the combustion chamber, and how much exergy is leaving. So ideally inlet exergy should be equal to the outlet exergy, but because of the irreversibilities within the combustion chamber, the exergy will be destroyed. So again we will see that how much exergy is destroyed in the combustion chamber. So same we will apply on the gas turbine, that how much is the input exergy, how much is the leaving exergy, and how much is the difference, right? So because of the difference, there is exergy destruction within the gas turbine. So for these three components, we'll try to draw a graph, one for the compressor, one for the combustion chamber, one for the gas turbine. So we'll see that which component has the highest amount of the exergy destruction. So we'll focus that component, right? We'll try to focus that component, that why our useful work, which is called exergy, is destroyed in that component, right? So then we'll try to dig out the reason why our useful work or the exergy has destroyed in, let's say, in turbine. So there could be many reasons, maybe because of the high friction. So we'll try to see whether the lubrication for the bearing is okay. Is there any vibration in the gas turbine? Or it could be because of the heat loss. So there could be poor insulation for the gas turbine. So there could be countless reasons for the loss of the exergy, right? This is the one significance of the exergy, that you can analyze each component of the system, that in each component how much is the loss in exergy. Loss in exergy means loss in useful work. Similarly, in second example, I would say, like in steam turbine, let's say in that example it has four component: boiler, steam turbine, condenser, and the pump. So again, For each component, we'll try to calculate the exergy loss, that how much is the inlet exergy, how much is the outlet exergy. So within the system there will be irreversibilities, and because of those irreversibilities there will be destruction in exergy. So we'll try to calculate the exergy in the pump. Similarly, we'll try to calculate how much is the exergy loss in boiler, how much is the exergy loss in steam turbine, similarly how much is the exergy loss in condenser. So for these four components, we'll try to calculate, we'll try to draw a graph, one for the boiler, one for the steam turbine, one for the condenser, one for the pump. So we'll focus in those components where the loss of the exergy is very high, and then we'll try to dig out the reason why our useful work has it destroyed in these components, right? So this is the significance of the exergy, that why we want to learn the new concept. So from the energy analysis, now we can shift to the exergy analysis. So exergy analysis will give you the value of the loss in useful work as a result of the irreversibilities.